September 15, 1916, Flers-Courcelette, Somme Valley, France. Second Lieutenant Harold Mortimer of the Heavy Section. Machine Gun Corps pressed his face against the viewing slit of Tank D-17, struggling to see through the acrid smoke that filled the cramped interior. The temperature inside approached 110 degrees Fahrenheit. His uniform was soaked through with sweat, his hands slick on the hot metal as the 28-ton steel monster lurched across the cratered landscape. Through the narrow aperture, he watched British infantry advancing behind his vehicle, using it as a mobile shield against German machine gun fire that previously would have cut them down in windrows. The men looked different than they had at dawn. They moved with purpose rather than resignation, their faces showing something Mortimer had not seen in 2 years of trench warfare. Hope. The Mark I tank represented more than mechanical innovation. It embodied a fundamental shift in how military forces could approach the central problem of the Western Front: how to cross defended ground without unacceptable casualties. The technology addressed the brutal mathematics that had defined warfare since 1914. A single German MG-08 machine gun, properly positioned and supplied, could fire 400-500 rounds per minute to an effective range of 2,000 yards. Infantry advancing across open ground moved at approximately 3 miles per hour. The calculation was simple and merciless. What the tank offered was not invulnerability, far from it, but the possibility of closing with enemy positions while providing mobile cover for infantry and suppressing defensive fire. The specific technical challenge the tank addressed was the vulnerability of advancing troops to interlocking fields of machine gunfire and the inability of conventional artillery to neutralize fortified positions without destroying the ground that subsequent attacks needed to traverse. Prior to the tank's introduction, assault tactics relied on massive artillery bombardments lasting days or weeks, followed by infantry advances across ground, rendered nearly impassable by cratering. This approach telegraphed intentions, allowed defenders to bring up reserves, and frequently bogged down in the devastated landscape it created. Before tanks, the British Army's solution to crossing defended ground centered on artillery preparation and infantry tactics. The standard approach, refined through bitter experience on the Somme, involved preliminary bombardments of unprecedented scale. During the week preceding the July 1, 1916 Somme offensive, British guns fired approximately 1.7 million shells. The theory held that such bombardment would destroy German defensive works, cut barbed wire obstacles, and neutralize defending forces. In practice, the method proved inadequate for multiple reasons. The technical specifications of British artillery in 1916 revealed both impressive capability and inherent limitations. The standard 18-pounder field gun could fire an 18.5-pound high-explosive shell to a maximum range of 6,500 yards, delivering approximately 6 rounds per minute under optimal conditions. Heavier pieces, like the 60-pounder, fired 60-pound shells to 10,300 yards. However, the shells often failed to cut wire effectively. High-explosive rounds frequently threw barbed wire into tangled masses rather than destroying it, while shrapnel rounds proved ineffective against wire obstacles. Additionally, the preliminary bombardment destroyed drainage systems and churned the ground into a moonscape of overlapping craters that filled with water, creating an obstacle for the very forces the bombardment was meant to support. Training for infantry assault tactics in 1916 emphasized advancing in waves across no man's land, maintaining formation while crossing wire obstacles breached by artillery, and occupying German trenches. Soldiers practiced these movements repeatedly in training areas behind the lines. The limitations became apparent under actual combat conditions. Men carrying 60-70 pounds of equipment, rifle, ammunition, grenades, entrenching tools, rations, water, moved slowly across broken ground. When German machine gunners emerged from deep dugouts that survived the bombardment, they found ideal targets in the dense formations of advancing British troops. Combat. Effectiveness statistics from the first day of the Somme offensive documented the inadequacy of existing methods with brutal clarity. The British Army suffered approximately 57,470 casualties on July 1, 1916, including 19,240 dead. These figures represent the largest single-day loss in British military history. Available records indicate that German casualties on the same day numbered approximately 8,000. The disparity reflected the fundamental advantage of defensive positions, equipped with machine guns against infantry assault tactics, regardless of preliminary bombardment intensity. The tank's development originated not with military planners, but with civilians who recognized the technical challenge and proposed engineering solutions. Winston Churchill, then First Lord of the Admiralty, established the Landships Committee in February 1915 to explore tracked vehicle development. Parallel efforts by Lieutenant Colonel Ernest Swinton of the Royal Engineers, who had observed combat conditions in France, emphasized the need for an armoured vehicle capable of crossing trenches and wire obstacles while providing fire support. The initial design brief specified a vehicle that could cross an 8-foot trench, climb a 4.5-foot vertical obstacle, operate in 4 feet of water, and carry armaments sufficient to neutralize machine gun positions. William Foster and Currams of Lincoln produced the first prototype, designated Little Willie, in September 1915. This vehicle proved the basic concept feasible, but could not meet the trench crossing requirements. The second prototype, Mother, incorporated a rhomboidal track system that extended around the vehicle's entire length, distributing weight and enabling it to cross wider obstacles. Tested in February 1916, Mother successfully demonstrated its ability to cross an 8-foot trench and navigate broken ground that would stop wheeled vehicles. The British Army ordered 100 production tanks in February 1916 under conditions of extreme secrecy. To disguise their purpose during manufacture and shipment, they were designated as water carriers, or tanks, for the Russian front, hence the name that became standard. The heavy section, Machine Gun Corps, received responsibility for manning and operating the vehicles, drawing personnel from infantry regiments and mechanical trades. Production tanks designated Mark I came in 2 configurations. Male tanks carried 2 6-pounder guns, 1 in each side sponson, plus 3 Hotchkiss machine guns, providing firepower against hardened targets. Female tanks mounted 5 Vickers machine guns designed for anti-personnel work and infantry support. Both variants weighed approximately 28 tons fully, loaded, and were powered by a Daimler Knight 6-cylinder sleeve valve, engine producing 105 horsepower at 1,000 RPM. The Mark I's physical dimensions reflected its design priorities. Overall length measured 32 feet 6 inches, with a width of 13 feet 9 inches across the sponsons. Height reached 8 feet. The rhomboidal track system extended nearly the entire length of the vehicle, with each track measuring approximately 26 feet in circumference and 20 inches in width. This configuration distributed the vehicle's 28-ton mass across approximately 40 square feet of ground contact area, resulting in ground pressure of approximately 14 pounds per square inch, comparable to a human foot and significantly lower than wheeled vehicles of similar weight. Inside the Mark I, conditions tested human endurance as severely as enemy fire. The crew compartment occupied a space approximately 10 feet long, 6 feet wide, and 5 feet high at its maximum. 8 men operated each tank: commander, driver, 2 gearsmen, 1 for each track, and 4 gunners. The driver sat forward, operating the main engine throttle and brake. The gearsmen, positioned amidships, operated separate gearboxes for the left and right tracks. Steering required coordination between driver and gearsman, with the driver signalling desired direction and the gearsman adjusting track speeds accordingly. This system proved cumbersome. A 90-degree turn required approximately 50 feet of space and left the vehicle vulnerable while maneuvering. The engine's placement directly in the crew compartment, without effective soundproofing or heat shielding, created a brutal working environment. Engine noise exceeded 100 decibels, making verbal communication impossible. Crew members communicated through hand signals or by hitting each other to get attention. The sleeve valve engine and exposed metal surfaces radiated heat that, combined with poor ventilation, regularly pushed interior temperatures above 100 degrees Fahrenheit, even in moderate weather. Exhaust fumes accumulated in the compartment, causing frequent nausea and headaches. Carbon monoxide poisoning represented a constant hazard. Crews typically operated while partially overcome by fumes, reducing reaction times and judgment. Armor protection consisted of steel plates varying from 6mm to 12mm thickness, sufficient to stop rifle and machine gun bullets at typical combat ranges, but vulnerable to armor-piercing ammunition and field artillery. The armor's hardened steel composition made it prone to spalling. When bullets struck the exterior, metal fragments broke off the interior surface at high velocity, creating a shrapnel effect inside the crew compartment. Crew members wore face masks with chain-mail visors to protect against spalling. But these restricted vision and breathing in an already oppressive environment. breathing in an already oppressive environment. Manufacturing the Mark I tanks challenged British industrial capacity. Each vehicle required approximately 5,000 man-hours to construct and consume materials that could otherwise produce several artillery pieces or hundreds of rifles. The suspension system alone involved precision engineering. Each track consisted of 90 plates, weighing approximately 60 pounds each, connected by pins that required exact tolerances to prevent binding or separation under load. William Foster & Co.'s facilities could produce approximately 3 tanks per week at peak output, with Metropolitan Carriage, Wagon and Finance Company of Birmingham providing additional production capacity. Critical components posed particular manufacturing difficulties. The Daimler engine, adapted from pre-war commercial designs, required extensive modification for military service. Cooling systems needed to operate reliably, despite obstructed airflow and accumulated mud. The transmission system, originally designed for lighter vehicles, required strengthening to handle the tank's weight and ground resistance. Each gearbox contained approximately 180 individual parts that required precision machining. Quality control became essential. A single defective gear could immobilize a tank, and field repairs often proved impossible under combat conditions. The Heavy Section, Machine Gun Corps, formed at Elvedon in Norfolk during early 1916 to operate the new tanks. The service selected officers and enlisted men based on technical aptitude and initiative rather than traditional military credentials. Many came from mechanical trades, engineers, mechanics, electricians, bringing practical skills applicable to maintaining and operating complex machinery. This represented a significant departure from conventional military organization, which typically assigned technical specialties lower status than combat arms. Training emphasized mechanical operation, maintenance, navigation, and gunnery. Crews spent weeks learning to drive the vehicles, practicing turns, obstacle crossing, and operating in various terrain. The coordination required between driver and gearsman demanded extensive practice. Improper timing could strip gears, break tracks, or leave the vehicles circling helplessly. Navigation training addressed the particular challenge of maintaining direction when visibility was limited to narrow viewing slits and the interior filled with smoke and fumes. Crews learned to navigate by compass, counting revolutions of landmarks, and dead reckoning, skills typically associated with naval operations rather than ground combat. The first combat deployment of tanks occurred on September 15, 1916, during the Somme offensive's later stages. C Company, Heavy Section, Machine Gun Corps committed 36 Mark I tanks to support the attack toward Flers-Courcelette. The deployment reflected compromise between advocates who wanted to wait for larger numbers and commanders demanding immediate employment to support faltering Somme operations. Available records indicate that of the 36 tanks that started toward the front lines, only 32 reached the start positions. 4 broke down before entering combat. Of those 32, 9 successfully crossed no man's land and contributed meaningfully to the attack, while the remainder bogged down, suffered mechanical failure, or fell victim to artillery fire. Despite the modest numbers, tanks that reached German positions achieved dramatic local effects. Second Lieutenant Harold Mortimer's D-17 supported the 6th Battalion, King's Own Yorkshire Light Infantry in their assault on Flers. His after-action report, preserved in the Tank Museum archives, describes the action. We proceeded across no man's land at approximately 2 miles per hour, receiving machine gun fire that had no effect against our armour. Upon reaching the German wire, we turned parallel to their trench line and proceeded along it, firing into the trench with our starboard sponson gun. The infantry followed at perhaps 50 yards distance, advancing without the severe casualties we had observed in previous actions. Enemy soldiers abandoned their positions in apparent panic at our approach. Similar accounts appeared in reports from other tank commanders. Captain H.W. Mortimer of D Company noted, "The moral effect upon enemy infantry appears substantial. German soldiers frequently abandoned serviceable defensive positions upon observing our approach, even when they retained capability to inflict casualties upon our supporting infantry." This psychological impact proved as significant as the tank's physical effect on enemy positions. German soldiers had adapted to artillery bombardment, machine gun fire, and infantry assault through 2 years of combat. The tank presented something fundamentally different: an invulnerable, or apparently invulnerable, mobile fortress that could not be stopped by small arms fire. British infantry reactions varied, but uniformly reported increased confidence when tanks supported their advance. Private Robert Tate of the 47th Division wrote in a letter preserved at the Imperial War Museum, "When we saw these monsters coming up behind us, there was a feeling like nothing I can describe. We had gone over the top before and knew what to expect, the machine guns, the wire, the shells, but now we had something that could fight back, something the Jerrys couldn't stop with their guns. Men who had been certain they would die that day suddenly believed they might survive." The German response to tanks reflected surprise, followed by rapid tactical adaptation. Initial encounters produced confusion and local panics. German forces lacked doctrine for engaging armoured vehicles and found their standard small arms ineffective. However, German army methodical analysis of captured tanks and interrogation of prisoners quickly revealed the vehicle's vulnerabilities. Field artillery firing over open sights could penetrate tank armour at close range. Armour-piercing machine gun ammunition, developed for use against steel shields and loopholes, proved effective against the Mark I's thin armour. Mechanical reliability represented perhaps the greatest weakness. German forces learned that tanks broke down frequently and could often be bypassed. Rather than engaged, German tactical circulars issued in October 1916 instructed units facing tanks to maintain discipline, hold positions, and engage with available weapons. Artillery crews received orders to position guns for direct fire against tanks. Infantry learned to target vulnerable points, vision slits, track mechanisms, and the vehicle's roof, which featured thinner armour than the sides. Perhaps most importantly, German commanders recognized that tanks required infantry support to be effective. If defending forces could separate tanks from their supporting infantry through artillery fire or counterattacks, the isolated vehicles became vulnerable to close-range attack, or could be bypassed and reduced later. The psychological adaptation proved equally important. After initial shock subsided, German soldiers learned that tanks could be destroyed or disabled through determined resistance. Several German soldiers received recognition for attacking tanks at close range with grenades, explosives, or field guns. These actions, publicized through army newspapers and citations, helped normalize the tank as a dangerous but not invincible weapon. By late 1916, German forces had integrated anti-tank tactics into standard doctrine and no longer treated tanks as an overwhelming threat. The September 15, 1916 action provided valuable lessons that influenced subsequent tank employment. Mechanical reliability emerged as the most critical issue of 49 tanks that deployed for operations in September and October 1916. Mechanical failures eliminated more vehicles than enemy action. The heavy section established forward workshops to conduct repairs closer to the front lines, reducing the time tanks spent out of service. Spare parts supply chains needed development. Each tank required unique maintenance, and critical components often proved unavailable when needed. Navigation difficulties highlighted the need for improved crew training and better communication systems. Tank commanders found maintaining direction nearly impossible once inside the vehicle, especially when smoke and fumes obscured what limited visibility the viewing slits provided. External marking systems and pre-arranged signal procedures helped but never entirely solved the problem. The coordination required between tanks, supporting infantry, and artillery demanded extensive rehearsal and clear communication, all difficult to achieve in the chaotic environment of combat. The Somme experience, while tactically limited, proved the tank concept viable and justified continued development. The British Army ordered 1,000 additional tanks in October 1916, with improved Mark II, III, and a full variants incorporating lessons from combat experience. The Mark IV, which became the primary British tank model in 1917, featured improved armour, 12-metre maximum thickness, better ventilation, external fuel tanks, reducing fire hazard, and simplified sponson design that could be removed for rail transport. Throughout late 1916 and early 1917, the Tank Corps, redesignated from Heavy Section in July 1917, expanded and refined its doctrine. Training emphasized combined arms cooperation, with tanks, infantry, and artillery practicing coordinated assaults. The tank's slow speed, approximately 3.7 miles per hour, maximum on roads, less cross-country, required infantry to advance at a deliberate pace rather than rushing forward. Artillery fire plans needed modification to avoid hitting friendly tanks while suppressing enemy positions. The Battle of Arras in April 1917 saw increased tank employment, with 60 tanks supporting the assault. Results remained mixed. Mechanical reliability continued to plague operations, with approximately 40% of tanks suffering breakdown before or during combat. However, where tanks successfully supported attacks, they contributed to significant advances. The Canadian Corps' assault on Vimy Ridge incorporated 9 tanks, which helped infantry overcome particularly stubborn German defensive positions that had resisted capture in previous operations. The tactical situation in Flanders during spring and summer 1917 proved particularly unsuitable for tank operations. The Third Battle of Ypres, commonly known as Passchendaele, featured waterlogged terrain that negated the tank's cross-country capability. Tanks frequently bogged down in mud, becoming stationary targets for German artillery. Of 48 tanks committed at the Battle of Pilkem Ridge on July 31, 1917, only 19 reached their start positions, and all of those either bogged down or suffered mechanical failure. The Passchendaele campaign reinforced the principle that tanks required firm ground to operate effectively, a lesson that would influence the selection of battlefield terrain for the next major tank operation. The Battle of Cambrai, launched on November 20, 1917, represented the first large-scale tank attack conducted under conditions chosen to maximize the vehicle's effectiveness. The Tank Corps staff, working with 3rd Army headquarters, selected the Cambrai sector specifically for its suitability for tank operations. The ground was relatively firm chalk downland, not heavily cratered by previous fighting. German defences included the formidable Hindenburg Line, but consisted primarily of trench systems and wire obstacles, rather than extensive fortifications requiring heavy artillery bombardment to reduce. Most importantly, the plan called for surprise, no preliminary bombardment that would churn the ground and alert defenders. General Hugh Ells, commanding the Tank Corps, concentrated 476 fighting tanks and 32 supply tanks for the assault, the largest tank force assembled to date. The plan called for tanks to advance in sections of 3, with the first tank crossing the German wire and advancing partway across the trench, where it would turn and proceed parallel to the trench. The second tank would cross on the wire flattened by the first, turn the opposite direction, and engage the trench from the other side. The third tank would cross the trench using fascines, large bundles of wood carried on the tank's nose, and dropped into the trench to create a bridge, and proceed to attack the next defensive line. Infantry would follow closely, occupying trenches cleared by the tanks and consolidating gains. Preparation for Cambrai demonstrated the Tank Corps' evolution in tactical sophistication. Tank crews rehearsed the specific tactics using a mock-up of the German defences constructed behind British lines. Engineers developed improved fascines, standardizing dimensions, 10 feet in diameter, 4.5 feet long, and attachment mechanisms. The tanks assembled in secrecy, moving forward at night and remaining camouflaged during daylight hours. Supporting arms coordinated carefully. Artillery planned smoke screens and counter-battery fire without preliminary bombardment, while Royal Flying Corps aircraft would provide reconnaissance and ground attack support. The assault began at 6:20 a.m. on November 20th, 1917, with a hurricane artillery bombardment, intense but brief, coinciding with the tank advance. The surprise proved complete. German forces, expecting the relatively quiet Cambrai sector to remain static, suddenly faced hundreds of tanks emerging from morning mist. The psychological impact matched or exceeded that achieved on the Somme 15 months earlier, now amplified by the sheer number of vehicles and the absence of warning. Captain D.G. Brown, commanding B Battalion, 1st Tank Brigade, described the advance in his subsequent memoir. "We moved forward as rehearsed, our section proceeding toward the German wire. The enemy appeared stunned. Machine gun fire was sporadic and ineffective. Our tank crushed the wire as designed, and we saw infantry coming behind us, moving quickly and with minimal casualties. The carefully prepared German positions that had taken months to construct were penetrated in hours. Available records indicate that the initial assault achieved unprecedented success. The 51st Highland Division, supported by E and F battalions of the Tank Brigade, advanced approximately 4 miles, a gain that would have been remarkable in any First World War battle and was extraordinary for a single day's fighting. The 62nd Division, supported by tanks from C and D battalions, achieved similar penetrations. By evening of November 20th, British forces had penetrated the Hindenburg Line on a 6-mile front, captured 8,000 prisoners, and inflicted approximately 10,000 casualties, while suffering roughly 4,000 casualties themselves, a reversal of the typical casualty ratios that characterized Western Front combat. The tactical success, however, proved difficult to exploit. The Tank Corps had committed nearly its entire operational force, and casualties among the tanks proved severe. Of 476 fighting tanks that began the attack, approximately 65 were destroyed by enemy action, 71 broke down with mechanical failures, and 43 ditched or became otherwise immobilized. By the evening of November 20th, fewer than 100 tanks remained operational. The following days saw this number decline further as accumulated wear from extended operations caused additional breakdowns. German response to Cambrai evolved from the initial shock to methodical counteraction. General von der Marwitz, commanding the German Second Army, immediately called forward reserves and organized counterattacks. German artillery, particularly field guns positioned for direct fire, destroyed numerous tanks as they advanced beyond the initial breakthrough zone. The initial penetration had disrupted German defensive positions, but not broken the German army's capacity to respond. By November 22nd, German forces had stabilized the front and were preparing counterattacks. The German counteroffensive, launched on November 30th, 1917, employed new infiltration tactics developed on the Eastern Front. Stormtroop units bypassed strong points, penetrated into the British rear areas, and exploited gaps in the defensive line. This represented the German army's tactical evolution in response to the same challenges that British forces faced: how to break through prepared defences. The German counterattack recaptured most of the ground taken during the initial British assault, demonstrating that tactical success required sustainable operational capability, not merely initial breakthrough. Lieutenant Clement Robertson of the 3rd Battalion, Tank Corps, participated in both the initial assault and the desperate defence during the German counterattack. His account, preserved in the Tank Museum archives, illustrates the complexity of tank operations beyond the initial breakthrough. After 3 days of operations, my tank crew was exhausted. The fumes, heat, and constant mechanical troubles had worn us down more than enemy action. When the Germans counterattacked, we had perhaps 30 operational tanks to defend a 6-mile front. We did what we could, firing from static positions as the enemy advanced. The tank proved valuable in defense as well as attack, but mechanical reliability remained our greatest enemy. The Battle of Cambrai demonstrated both the potential and limitations of tank warfare as practiced in 1917. The initial assault proved that, properly employed, tanks could break through prepared defenses when concentrated in sufficient numbers and supported by effective combined arms tactics. The subsequent inability to exploit this success and the German counteroffensive illustrated that technological superiority in one weapon system could not compensate for inadequate reserves, limited mobility, and mechanical unreliability. Statistical analysis of Cambrai reinforces these conclusions while highlighting the challenges of quantifying technological impact. British casualties for the entire Cambrai operation, November 20th to December 7th, totaled approximately 44,000, while German casualties numbered roughly 45,000, representing approximate parity rather than the attacker's usual significant disadvantage. Tank availability provides a more precise metric. Of 476 tanks committed on November 20th, approximately 92 remained operational by November 27th, an 81% loss rate over 7 days. Available records indicate enemy action accounted for approximately 27% of tank losses, with mechanical failure causing 30% and ditching or other operational losses accounting for 24%, with the remainder unspecified in surviving documents. The broader impact of tank development extended beyond immediate tactical results. The industrial effort required to produce tanks demonstrated British manufacturing capacity and adaptability. By November 1918, British industry had produced approximately 2,636 tanks of various models, requiring the equivalent labour of producing 5,000 aircraft or 800 artillery pieces. This production involved not merely assembly, but development of entirely new manufacturing techniques, quality control procedures, and supply chains for specialized components. The training infrastructure created for the Tank Corps established methodologies that influenced subsequent military technical training. The Tank Corps Central Workshops at Tanneur in France, established in 1917, employed approximately 800 men operating machine shops, forges, and specialized repair facilities capable of rebuilding tanks from salvaged components. This represented an unprecedented, forward-deployed industrial capability. The training schools at Bovington in England developed systematic instruction covering mechanical operation, tactical employment, maintenance, and combined arms cooperation. These programs emphasized technical proficiency and initiative to a degree unusual in First World War military. Training tactical doctrine evolution reflected the experience gained through successive tank operations. By 1918, British doctrine recognized tanks as one component of combined arms operations rather than an independent breakthrough weapon. Infantry, artillery, tanks, and aircraft required careful coordination, with each arm supporting the others. The 100 Days Offensive from August to November 1918 demonstrated this mature doctrine. At the Battle of Amiens, beginning August 8, 1918, 414 tanks supported the assault alongside Australian and Canadian infantry, with carefully coordinated artillery support and air superiority. The result, advances of up to 7 miles on the opening day, represented the culmination of 4 years' tactical evolution. Individual experiences throughout the tank's combat development reveal how technology and human adaptation interacted. Second Lieutenant Harold Mortimer, who commanded D-17 on September 15, 1916, continued serving in the Tank Corps through the war's conclusion. His progression from uncertain experimentation to confident expertise mirrors the institution's evolution. Promoted to captain by November 1918, Mortimer commanded a company at the Battle of Cambrai and the subsequent 1918 offensives. His later writings, now in the Tank Museum collection, reflect on the transformation. What seemed impossible in 1916, crossing defended ground with acceptable losses, had become routine by 1918. The tank contributed to this transformation, but only as one element in a system that included improved artillery tactics, infantry training, air support, and above all, the gradual accumulation of hard-won experience. Lieutenant Robertson's career followed a different trajectory, but reached similar conclusions. Wounded during the German counterattack at Cambrai when his tank was hit by armor-piercing rounds, Robertson returned to duty in March 1918. He commanded a tank platoon during the Battle of Amiens and received the Military Cross for actions on August 8, 1918, when his section of 3 tanks supported Australian infantry in capturing the village of Proyart, despite heavy casualties. His post-war career continued in armoured warfare development. He served as an instructor at Bovington and contributed to interwar tank doctrine. His 1924 lecture notes, preserved in the British Army archives, emphasised, "The tank of 1918 was not fundamentally different from that of 1916 in basic capability. What changed was our understanding of how to employ it effectively within combined arms operations." Sergeant Arthur Williams provides a third perspective from the enlisted ranks. Williams, a pre-war mechanic, joined the heavy section in April 1916 and served as a driver throughout the war. His technical expertise proved invaluable. He conducted field repairs that kept tanks operational under conditions that would typically require workshop facilities. Williams participated in actions from Flers-Courcelette through the 100 Days, surviving multiple tank casualties and earning the Distinguished Conduct Medal. His post-war employment with the Tank Museum, where he maintained the historical vehicle collection, provided continuity between wartime service and institutional memory. Interviews conducted in the 1950s captured Williams' perspective. The tanks were difficult machines, always breaking down, always needing repair, but they gave infantry a chance they didn't have before. That made the heat, fumes, and danger worthwhile. The post-war evolution of tank technology built directly on First World War experience, while addressing recognized limitations. The medium Mark A Whippet, introduced in 1917, sacrificed armor and armament for improved speed, approximately 8 miles per hour, and reliability, providing reconnaissance and exploitation capabilities. The Mark V tank, also introduced in 1917, incorporated significantly improved transmission design, allowing one driver to control the vehicle without separate gearsmen, a fundamental improvement in usability. These developments reflected systematic problem-solving addressing specific operational deficiencies identified through combat experience. Interwar tank development continued this evolutionary process. The Vickers medium Marks I and II, entering service in the early 1920s, featured improved suspension, more powerful engines, and better crew arrangements that acknowledged the human factors largely ignored in wartime designs. These vehicles influenced tank development globally: the Soviet T-18, the Japanese Type 89, and various European designs drew on British interwar tank concepts. The United States, which had deployed no American-designed tanks during the First World War despite planning substantial production, based its initial post-war tank development on British and French models. Medium Mark I represented the synthesis of wartime, lessons into a practical design optimized for the realities of mechanized warfare rather than trench combat. Weighing approximately 12 tons versus the Mark V's 29 tons, the Medium Mark I achieved speeds up to 15 miles per hour and featured a fully rotating turret mounting a 3-pounder gun and machine gun. The crew of 5 occupied positions designed with some attention to ergonomics. The driver sat forward with improved visibility. The commander occupied the turret with better situational awareness, and the engine compartment was somewhat better isolated from crew spaces. These improvements, modest by later standards, represented substantial progress from the Mark I's brutal working conditions. The integration of tanks with other technologies transformed combined arms warfare throughout the interwar period. Wireless communication, primitive during the First World War, became standard equipment on tanks by the late 1920s, dramatically improving coordination. Motorized infantry and artillery could now move at speeds compatible with tanks, enabling exploitation of breakthroughs that would have stalled in 1917 and 1918. Anti-tank weapons evolved simultaneously. Specialized guns, improved ammunition, and dedicated anti-tank units reflected the permanent place of tanks in military planning. This technological dialogue, innovation driving counter-innovation, characterized military development through the remainder of the 20th century. The doctrinal legacy of First World War tank operations influenced military thinking far beyond the specific technology. British theorists like J.F.C. Fuller and B.H. Liddell developed concepts for mechanized warfare that envisioned tanks as decisive weapons capable of deep penetration and operational paralysis of enemy forces. While these theories often exceeded technological capabilities of interwar tanks, they influenced development in Britain, France, Germany, and the Soviet Union. German development of blitzkrieg tactics, which proved devastatingly effective in 1939-1941, built directly on British tank warfare concepts, combined with improved technology and more aggressive operational concepts. The question of whether tanks changed warfare forever, as later assessments claimed, requires careful examination of available evidence and appropriate qualification of claims. What can be documented is that tanks contributed to breaking the tactical stalemate of the Western Front when employed as part of effective combined arms operations. The 100 Days Offensive from August to November 1918 achieved the most sustained and significant Allied advances of the war, approximately 70 miles of advance, the liberation of occupied France and Belgium, and ultimately German acceptance of armistice terms. Tank operations formed one component of this success, alongside improved artillery tactics, more effective infantry training, superior logistics, accumulated Allied material advantage, German exhaustion, and numerous other factors. Quantifying the specific contribution of tanks to this success remains difficult with available data. British forces conducting attacks with tank support in 1918 generally achieved deeper advances with lower casualties than comparable attacks without tanks. But separating tank impact from improvements in artillery, infantry tactics, and overall operational proficiency proves challenging. What testimony uniformly reported was increased infantry confidence and improved casualty ratios when tanks were present, outcomes difficult to measure precisely but significant nonetheless. The psychological impact of tanks on both friendly and enemy forces represented perhaps their most immediate effect. German soldiers never became entirely comfortable with tank attacks even after developing effective anti-tank tactics. British infantry consistently requested tank support when available and demonstrated greater willingness to advance when tanks were present. These psychological effects, while difficult to quantify precisely, influenced tactical outcomes measurably. Attacks that achieved surprise and featured tank support typically penetrated German defences more quickly and captured more prisoners than attacks lacking these elements, suggesting that the mere presence of tanks affected German willingness to resist. The collaborative nature of the tank's development and employment deserves emphasis as perhaps the most significant lesson. No individual invented the tank. It emerged from multiple parallel efforts by civilian engineers, military officers, industrial manufacturers, and frontline soldiers who identified the problem and contributed to solutions. The Landships Committee, William Foster and Co., the heavy section's officers and men, supporting arms commanders who integrated tanks into operations, and logistics personnel who maintained supply chains all contributed essential elements. This represented warfare's evolution from an art dependent on individual genius to an industrial enterprise, requiring systematic organization and collective effort. The transition from regarding warfare as primarily a test of individual courage and tactical skill to recognizing it as a complex system requiring technological, industrial, and organizational superiority characterized First World War military development broadly. The tank exemplified this transition. It was not a weapon that skilled individuals wielded, but a complex machine requiring specialized training, systematic maintenance, and integration into carefully planned operations. The heavy section, Machine Gun Corps, began as a novel experiment grafting mechanical specialists into a military organization designed for different purposes. By war's end, the Tank Corps had established itself as a permanent component of military forces, with its own doctrine, training infrastructure, and institutional culture. The incremental nature of the tank's impact deserves recognition alongside its revolutionary potential. The Mark I of September 1916 and the Mark V of 1918 were not dramatically different machines in basic capability. Both moved at approximately 4 miles per hour, carried similar armament, and required substantial infantry support. What changed was understanding how to employ the technology effectively. Early operations treated tanks as independent breakthrough weapons. Later doctrine integrated them carefully into combined arms operations, using tanks to suppress enemy fire, while infantry and artillery neutralized anti-tank defenses. This evolution from revolutionary concept to routine component of military operations represents a common pattern in technological adoption, the human-machine partnership that tanks required. Highlighted tensions between technological and human factors. Tanks gave crews protection from small arms fire, while exposing them to unprecedented physical stress, heat, fumes, noise, and vibration that degraded performance and endangered health. Crews compensated through exceptional determination and skill, operating vehicles that contemporary industrial safety standards would have deemed uninhabitable. This created an ironic situation where advanced technology depended on human endurance that exceeded what could reasonably be expected. Post-war tank development gradually addressed these human factors, but the fundamental tension between protective capability and habitability persisted through subsequent tank generations. The institutional memory preserved through the Tank Museum at Bovington and regimental histories maintained continuity between wartime experience and peacetime development. Veterans like Sergeant Williams, who transitioned from combat service to museum roles, provided direct links to operational experience that might otherwise have been lost. The museum's collection, begun in 1923, preserved not merely vehicles but documentation, after-action reports, personal accounts, technical specifications, and maintenance records that enabled systematic study of what had worked and what had failed. This institutional approach to learning from experience represented a significant advance over previous practices, where military knowledge often died with the generation that acquired it. The Americans, arriving in France in 1917-1918, adopted British and French tank designs while planning substantial indigenous production. The United States Tank Corps, established in January 1918, trained initially with British Mark V and French Renault FT-17 tanks. American industry prepared to manufacture both types under license. The Mark VIII Liberty tank, designed jointly by British and American engineers, would have combined British mechanical design with American manufacturing methods. Production facilities at Rock Island Arsenal planned to deliver 1,500 Liberty tanks by mid-1919. The armistice rendered these plans moot. No American-designed tanks reached France before November 1918. However, the planning process and infrastructure development established American capacity for armored vehicle production that would prove significant in subsequent decades. Colonel George S. Patton, commanding the United States Tank Corps in France, absorbed lessons from British and French experience while developing distinctly American perspectives on armored warfare. Patton emphasized aggressive employment and exploitation of success, concepts that would characterize his later career. His training methods drew on British Tank Corps practices while incorporating American approaches to leadership and initiative. The 304th Tank Brigade, which Patton commanded at the Battle of Saint-Mihiel in September 1918, employed French Renault tanks in support of infantry assault, achieving local successes that validated the combined arms approach while demonstrating the continuing limitations of tank reliability and speed, the technological limitations that constrain tank operations. Throughout the First World War, shaped interwar development priorities. Mechanical reliability received sustained attention. The 40–50% breakdown rate typical of major operations in 1917–1918 was unacceptable for sustained mobile warfare. Engine development focused on improving power-to-weight ratios while enhancing durability. Suspension systems evolved to reduce crew fatigue and enable higher speeds across broken ground. Communication systems progressed from hand signals and message flags to wireless sets, fundamentally altering command and control possibilities. Each improvement addressed specific deficiencies documented through combat experience. The question of armor protection versus mobility drove design debates throughout the interwar period. The Mark I's armor, adequate against rifle and machine gun fire in 1916, became marginal as armor-piercing ammunition proliferated. Increasing armor thickness added weight, reducing speed, and increasing ground pressure. This fundamental trade-off, protection versus mobility, defined tank design choices through subsequent generations. Different nations emphasized different solutions. British interwar designs generally favored mobility and mechanical reliability, accepting lighter armor. French designs often prioritized protection, producing heavily armored but slower vehicles. German development, initially constrained by Versailles Treaty limitations, ultimately synthesized both approaches in the designs that dominated early Second World War operations. The doctrinal questions proved equally contentious and consequential. Should tanks operate independently as exploitation forces, breaking through and disrupting enemy rear areas, or should they remain subordinated to infantry support, moving at foot pace to provide direct fire support? British theorists divided on these questions, with Fuller advocating independent armoured operations and more conservative voices insisting tanks existed primarily to support infantry assault. The institutional outcome, separate tank brigades for exploitation alongside infantry tank battalions for direct support, represented compromise rather than resolution. This organizational ambiguity reflected genuine uncertainty about optimal employment methods given technological constraints and tactical possibilities. The Spanish Civil War, 1936–1939, provided the first significant combat test of interwar tank developments and doctrine. Soviet T-26 and BT-5 tanks supporting Republican forces faced German Panzer I tanks and Italian CV-33 tankettes supporting nationalist forces. The operations demonstrated that First World War lessons remained valid. Tanks required infantry and artillery support. Mechanical reliability was essential, and combined arms coordination determined outcomes more than any single weapon's characteristics. They also revealed that anti-tank guns had evolved more rapidly than armor protection. The German 37mm PaK-36 anti-tank gun could penetrate any tank then in service at typical combat ranges. This technological dialogue between armor and anti-armor weapons would continue indefinitely. The Second World War's opening campaigns vindicated some First World War tank concepts while revealing how much remained uncertain. German operations in Poland, 1939, and France, 1940, demonstrated that properly coordinated mechanized forces could achieve operational breakthroughs reminiscent of but far exceeding Cambrai initial success. However, these operations succeeded through combined arms excellence and operational planning, at least as much as through technological superiority. German tanks in 1940 were not dramatically superior to French or British equivalents in armor protection or armament. What differed was doctrine, training, communication systems, and aggressive exploitation of success. These represented the culmination of lessons that began with First World War tank operations. The continuity between First World War innovation and subsequent development extended beyond specific technologies to methodologies for military innovation itself. The process that produced the tank, civilian initiative, military experimentation, industrial adaptation, combat testing, systematic analysis, and iterative improvement became the model for developing subsequent military technologies. The Landships Committee's approach of bringing together diverse expertise to solve specific military problems anticipated the organization of later research and development institutions. The Tank Corps' emphasis on technical, training and initiative-based leadership influenced how modern militaries recruit and train personnel for technical specialties. The limitations and failures First World War tank operations proved as instructive as successes. The Passchendaele campaign's unsuitable terrain, Cambrai's inadequate exploitation planning, and persistent mechanical reliability problems throughout 1916-1918 highlighted that technology alone could not overcome operational and strategic shortcomings. These lessons, when remembered, prevented over-optimistic expectations about future technologies. When forgotten, as they periodically were, they required painful relearning. The cycle of revolutionary expectation, disappointing reality, systematic improvement, and eventual integration that characterized tank development would repeat with jet aircraft, helicopters, precision munitions, and numerous other technologies. The individuals who operated tanks during the First World War, men like Mortimer, Robertson, and Williams, experienced warfare's transformation from personal combat to industrial process. They began their service in an army where individual courage and small unit tactics determined outcomes. They ended it operating complex machines requiring technical expertise and functioning within elaborate combined arms systems. Their adaptation to these changed circumstances represented human flexibility in response to technological change. Their testimony, preserved in archives and regimental histories, provides insight into how ordinary men managed extraordinary demands while maintaining effectiveness, under conditions that should have exceeded human endurance. The post-war careers of these men illustrate how military innovation creates lasting institutional change. Mortimer remained in the Tank Corps, eventually retiring as a lieutenant colonel in 1932 after contributing to interwar doctrine development. His perspective, shaped by having commanded tanks from first combat employment through mature operational use, influenced the generation of officers who would command armoured forces in the Second World War. Robertson's technical expertise made him valuable as an instructor and doctrine writer. His contributions to training publications ensured that lessons learned in 1916-1918 informed 1930s preparation. Williams's transition from combat crew member to museum technician preserved practical knowledge about maintaining and operating vehicles that might otherwise have been lost when the last Mark I tanks were scrapped. The broader industrial legacy extended beyond military applications. Manufacturing techniques developed for tank production, welding heavy steel plate, machining precision gears under volume production, quality control for complex assemblies, transferred to civilian industry. Engineers and skilled workers who gained experience in armored vehicle production brought expertise to peacetime manufacturing. The organizational methods developed to coordinate design, manufacturing, and field service for tanks influenced industrial management practices. While these indirect effects resist precise quantification, available evidence suggests significant technology transfer from military to civilian sectors during and after the First World War. The tank's place in broader military history requires balanced assessment. It was neither the war-winning weapon that enthusiasts sometimes claimed, nor the marginal innovation that skeptics suggested. The tank contributed meaningfully to breaking the tactical stalemate that characterized 1914-1917 Western Front operations, but only as one component of broader improvements in combined arms warfare. By November 1918, Allied forces had developed operational methods that could penetrate German defenses and exploit success, methods that integrated tanks with improved artillery tactics, better trained infantry, air support, and superior logistics. Removing any single element would have degraded but not eliminated this capability. The precise quantification of the tank's contribution remains impossible with available evidence. Records document that major Allied offensives in 1918 typically achieved deeper penetrations and lower casualty ratios than comparable 1916-1917 operations. But whether this resulted from tank employment, improved artillery methods, better infantry training, accumulated German exhaustion, Allied material superiority, or some combination cannot be definitively determined. What can be stated with confidence is that commanders consistently requested tanks when available. Troops expressed increased confidence when tanks supported their operations, and operations featuring tank support generally achieved better outcomes than those without such support, suggesting meaningful tactical value even if precise quantification remains elusive. The lessons about incremental versus revolutionary innovation prove particularly relevant. The tank appeared revolutionary in concept. A machine that could protect troops while crossing defended ground represented a fundamental departure from previous warfare methods. In practice, its impact emerged gradually through systematic improvement and integration into evolving operational methods. The Mark I of 1916 was primitive and unreliable. The Mark V of 1918 was moderately improved, but still fundamentally limited. Neither individually transformed warfare. What proved transformative was the cumulative effect of incremental improvements in the technology itself, in doctrine for its employment, in combined arms integration, in logistics support, and in crew training. This pattern, revolutionary concepts requiring years of incremental refinement before achieving significant impact, characterized most military innovations. The collaborative achievement that the tank represented deserves emphasis as perhaps the most significant lesson. Churchill's initiative, Swinton's operational insight, Foster's engineering, the heavy section's combat testing, supporting arms commanders' tactical integration, industrial workers' manufacturing effort, and logistics personnel's supply chain management all contributed essential elements. No individual or organization could have produced the tank independently. This reality contradicts simplistic narratives of military innovation driven by individual genius or breakthrough invention. Instead, it reveals innovation as a complex social process requiring diverse contributions and sustained institutional support. The human-machine partnership embodied in tank operations highlighted tensions that persist in modern warfare. Technology extended human capability while imposing unprecedented physical and psychological demands. Crews operated in environments, extreme heat, toxic fumes, deafening noise that degraded performance even as the machine they controlled gave them enhanced combat effectiveness. This paradox, where advanced technology depends on human performance under conditions that impair human capability, continues to challenge military equipment design. The gradual improvement in crew working conditions from the Mark I through subsequent generations represented recognition that effective human-machine systems require attention to human factors, not merely technical capability. The memory and mythology surrounding tanks reflect broader patterns in how societies remember military history. Popular accounts often emphasize dramatic innovation and revolutionary impact, creating narratives of technological determinism where new weapons win wars. More careful examination reveals messier realities, limited initial effectiveness, gradual improvement, integration into complex systems, and outcomes determined by multiple interacting factors rather than single causes. The tank's actual history, properly understood, provides more valuable lessons than the simplified myths, teaching about the challenges of innovation, the importance of systematic improvement, and the collaborative nature of military effectiveness. The institutional structures created to support tank operations, the tank corps, specialized training schools, forward repair facilities, supply chains for specialized parts, represented organizational innovations as significant as the technology itself. Modern military forces remain structured around similar principles. Technical specialists organized into dedicated units, systematic training programs, forward-deployed maintenance capability, and specialized logistics. These organizational patterns, established during the First World War to support tanks and other new technologies, became fundamental to how modern militaries function. The British Tank Corps' evolution from the improvised heavy section of 1916 to the professional force of 1918 demonstrated how military institutions adapt to accommodate revolutionary technologies while maintaining core military virtues. As the century progressed and the last First World War veterans passed away, the tank's symbolic significance evolved. Veterans' accounts emphasized the brutal reality, the heat, fumes, mechanical breakdowns, and desperate struggles inside cramped metal boxes. Later generations, lacking direct experience, often romanticized tanks as irresistible weapons that broke the trench warfare stalemate. The truth lay between these extremes. Tanks were fallible machines operated by exhausted men in terrible conditions, achieving modest tactical advantages that became significant when combined with other improvements. This reality, less dramatic than the mythology, provides more useful historical understanding. The concluding assessment must acknowledge both what can be documented and what remains uncertain. Available evidence establishes that tanks contributed to the tactical evolution that eventually enabled Allied victory on the Western Front. They improved infantry confidence, suppressed enemy defensive fire, and facilitated penetration of defensive systems when properly employed. The magnitude of this contribution relative to other factors, improved artillery methods, better infantry tactics, superior logistics, accumulated Allied material advantages, cannot be precisely calculated from surviving records. What remains clear is that by November 1918, Allied forces had developed combined arms methods that could overcome German defences, and tanks formed one component of these methods. The technological trajectory from the primitive Mark I to modern armoured fighting vehicles spans more than a century of continuous development. Each generation of tanks addressed limitations of predecessors while introducing new challenges. Modern tanks bear little physical resemblance to First World War vehicles, yet the fundamental concept, protected mobility enabling ground forces to close with and destroy enemy forces, remains unchanged. The problems that tanks were designed to solve in 1916, how to cross defended ground with acceptable casualties, how to suppress enemy fire while advancing, how to break through defensive systems, remain central to ground warfare. This continuity suggests that the tank addressed enduring military challenges rather than solving problems. Unique to trench warfare, the First World War, tanks' legacy extends beyond military applications to broader questions about technology, organization, and human adaptation. The process that produced the tank, identifying a specific problem, developing technical solutions, testing under operational conditions, systematic improvement based on experience, became a model for subsequent military innovation. The organizational structures created to support tank operations influenced how modern institutions manage complex technologies. The human adaptation required to operate early tanks demonstrated both human flexibility and the importance of designing systems that acknowledge human limitations. These broader lessons transcend the specific technology, providing insight into how societies develop, adopt, and integrate innovations that fundamentally alter existing practices. The men who crewed First World War tanks, facing heat, fumes, mechanical failure, and enemy fire in primitive machines, demonstrated courage distinct from but comparable to conventional infantry combat. Their contribution to military history lies not merely in operating a novel weapon, but in proving that revolutionary technologies could be integrated into military operations despite severe limitations. Their willingness to operate under conditions that should have been intolerable, combined with systematic institutional efforts to improve those conditions and employment methods, exemplified the human-machine partnership that characterizes modern warfare. They were neither helpless victims of industrial warfare nor invincible warriors wielding war-winning weapons, but soldiers adapting to changed circumstances while maintaining military effectiveness despite extraordinary challenges. The Battle of Cambrai and the broader history of First World War tank operations changed modern warfare not through revolutionary transformation, but through demonstrating that incremental innovation, properly supported and systematically improved, could address seemingly intractable military problems. The tank did not win the First World War, but it contributed meaningfully to breaking the tactical stalemate that had characterized 1914-1917. More significantly, it established patterns of military innovation, technical development, operational experimentation, combined arms integration, systematic improvement that influenced subsequent military evolution. The men who developed, built, and operated these primitive machines created more than a new weapon. They demonstrated how modern military forces could identify problems, develop solutions, and adapt operations to exploit new capabilities. That collaborative achievement, sustained through years of frustrating setbacks and gradual progress, represents the true legacy of the First World War tank and its most enduring contribution to military history.